All right, everybody. Welcome to the WTS, Boston Society of Civil Engineers combined tour of Boston bridges. And we're going to be talking about the Sachem Bridge, but we're not at the Sachem Bridge right now. We're at Post Office Square. I'm Reed,
I'm Allie.
and we're going to show you how a bridge like the Sachem Bridge works. The Sachem Bridge, I know a lot of people like to call it a suspension bridge, but it's not. It is
Cable stayed bridge.
right. And the big words in there is that it's got cables. So we're going to make a model of a bridge. These are cables. And stayed is just a fancy word for tied off. It means the whole bridge is tied off to towers by cables. So that's all it is. It sounds tricky if you hear it, but when you hear it put like that, hopefully it makes a little more sense. So me and Allie, at the same time, we're going to start building this bridge, and we're going to help each other out. So we're both going to start on this tower, and we're going to grab a small box first. And as you can see, when you look at the small boxes have short cables on them. Remember the one I just picked up had a long cable. And the short one, it's short because it'll be the shortest distance from the tower, which means it'll also be at the lowest spot. So we're going to take the carabiners and hook them on the holes. Then, see how this is on the cable and it can swing and gravity wants it to swing to the middle? And then I hash it out of it. And they come together. And then, in real life, it wouldn't be just a loop on a knob that holds it together. They would be tied together tightly with, there'd be solid cables coming through and tying them together for a run. And this, you see, they won't hang perfectly right now, but that's okay because this bridge is all about gravity doing its thing. After this, we're going to grab the medium length cables. And at the same time, if you want, do you guys want to start building the other tower and doing exactly what we're doing over there? And I'll just keep talking about this one. We go to the medium height, to the second level, hook in the carabiners. It swings in. You see how this wants to swing all the way into the pier, but it's blocked. And that's what the whole nature of this is. So the tower, as we put on the cables, it's getting more weight on the tower, and it's getting heavier, and it's taking a lot of weight. So that's one thing to think about. The cables are in tension, and if anybody on any test ever asks you whether a cable's in tension or whether it's in compression, the answer has to be tension, because you can't push on a rope. So, and this one is like that, but this one is adjustable.
Medium. Ooh.
So we get it like that, and this one is adjustable too. So I'll talk to you about that. In real life, the cables are actually also adjustable. It's not just a here thing. And we can actually tell what the tension is. We can shake it like a guitar tuner and see what the note is, and you can tighten and loosen those to get the right amount of tension for what you're doing. And also, they survey the roadway. But once it's put together, I'll show you even more about that and how you can change the shape of the roadway. And as you can tell, we really are in the city of Boston right now, working away. So nice to be outside. So this one a little tighter. That's the one. Someone played with that.
Are these adjustable as well?
Yep.
Perfect.
We'll adjust that one. Maybe I went a little too far with that one. Okay, and they're getting there on that end. So this kind of bridge, it's using an ancient technology. Really, it's the same kind of technology that we use for the masts and the sails on ships. See how it looks a lot like a sail, but there's one thing that's a lot different. But now the technology doesn't have anything to do with that. The big technology was, you see how this becomes very unstable? So if you were building a very long bridge, you'd have this effect where it's moving. And the big thing that was created was gantry cranes, that they mount a horizontal crane on here to hold this stable, locked onto the tower and stabilized, and keeping all this from swinging as they're building it. So now we're going to do the impossibility. In real life, these towers cannot move. But watch this. We're going to do magic. In real life, the tower is not a Christmas tree stand. In real life, that would not be how we would build it. We would build it by the ones for the Sachem Bridge, for example. They're 8-foot diameter steel tubes that are filled with concrete, but they're driven down and socketed into rock. Um, so as you can see now, all of a sudden, once you lock it up, I mean, not perfect, but good enough for today. You can see it makes a stable bridge that doesn't twist anymore once you lock it together. This middle part, when we're inspecting the bridge especially, this is what's going to be subjected to the most forces because it's taking in all that twisting. In real life, running about 120 feet, like 60 feet each direction, every 1 foot there's a cable in there pulled tight, locking this together in the middle, coming in. So that's how it all holds together. Now, if you can see, these are adjustable, and as this cable gets more tension or less tension, the shape of the bridge changes. And that's another thing in a real bridge we can check is if you survey the roadway shape better be what you're expecting it to be. And also, the nice thing about this bridge versus suspension bridge is, on a suspension bridge, if one of the cables goes, the whole bridge goes. But on this bridge like this, and that one has many, many more cables than this, a couple of them could go. Yeah, figures. I put one at the end. Let's not take one at the end because that's a bad choice. But this one, the bridge will still be hanging there. The cables adjacent to it will pick up the force. And there's a lot of cables. You have something called redundancy. So this is just a little primer on how a bridge like the Sachem Bridge, a cable stay bridge, functions. Thank you, everybody.